So we're talking about infrared spectroscopy, which is a characterization method that we use in chemistry to determine what functional groups are present. And I was telling them how this thing works, like the theory behind it. And one of the things that to think about is like if two atoms are connected, the bond between them is always vibrating, but the atoms are like the bond is like a spring that the atoms are attached to, so it's always vibrating. So if you have two atoms connected to a bond that are vibrating, right, they kind of have a specific frequency, right, that they vibrate at. So they're vibrating and doing their own thing. And then in the infrared instrument, what happens is you bombard this sample with uh, infrared radiation. So you just keep hitting it with this radiation, but the bond never becomes excited until the frequency of the radiation matches the frequency that the bond is already vibrating at. So in other words, the radiation and the bond vibration have to be on the same wavelength in order for that bond to get excited. So the example that I used is here, right? So if I hit this with 100 nanometer radiation, then the bond, nothing happens. The bond doesn't get excited. It doesn't absorb the energy. If I hit it with 200, it doesn't get excited. Like that energy just passes through because the frequency that the bond is vibrating at is different than that radiation. If I hit it with 300, right, again, nothing happens. Why? Because the frequencies don't match. But when the frequencies match, that's when the bond gets excited. So when I hit this thing with 400, you'll see the difference, right? There's a little bit more excitement between those two atoms and they start vibrating faster.
Okay, so some of the different molecular motions that are possible. If you think about bonds as atoms, well, bonds between atoms as springs, and the atoms bonded together are able to kind of move as they're attached to those springs, right? Bonds and molecules are always vibrating. And so the infrared we just talked about, it intensifies the motion that's already occurring if the frequency of the infrared radiation matches the frequency of the vibration of the bond. So there are other types of molecular motion. If you irradiate a molecule, it can stretch, or you can see the two bonds here, here, and here are going in opposite directions. That's called stretching. All right, you can have bending, where the two blue atoms are moving in a downward direction, which in turn causes the red atom to move up. And then you can also have twisting, where the entire molecule can kind of rock back and forth, right? Where you can imagine grabbing the blue atom on the right and the blue atom on the left, and kind of turning them like kind of like if you were riding a bike, turning the handlebars, kind of left to right. That's what twisting. That's the molecular motion of twisting. All right, so one of the important things about infrared is the stretching frequency, where you see certain functional groups show up, and that's what infrared does. By the way, infrared is a way to determine what functional groups are present. It does not tell you anything about the necessarily about how the functional groups are connected in the structure, but it does tell you what's there. If there's a ketone, if there's an alkene, if there's a nitrile, if there's an alkyne, those functional groups show up at different places on the infrared spectrum, right? And so for certain functional groups, right, you can look at sp3, sp2, and sp and look at the difference in the stretching frequencies, right? That's because the sp hybridized carbons are closer together because of the nature of the increase in electronegativity for sp hybridized atoms, right? And so those two carbons are closer together, makes that bond tighter, shorter, and much more difficult to stretch, right? And you can look at the difference in the wave numbers for the carbon-carbon triple bond. You can see that you go from 1200 to 1600 to 2200, and that means that the bond becomes more stiff, more difficult to stretch, those two atoms apart, and so it takes a lot more energy, right? All right, so here's some common functional groups. Alcohols show up between 32 and 3400. It's this broad stretch that's out here. All right. I'm just going to run through these. If you have a carbonyl, right, those carbonyls show up somewhere between 16 and 1800, and that's a pretty strong stretch as well. Here are the different carbonyl stretches for aldehyde. Of course, you got multitude of different types of carbonyls. So you have aldehydes, ketones, esters, acids, amides, right? And they all show up in the same range. It's very difficult to tell them apart. And again, infrared only tells you what's there. So you need another method, another spectroscopic method to determine this with specificity what's there, right? Infrared can tell you that there's a carbonyl present. And another thing that you have to keep in mind is that when most of the times if you do an experiment and you synthesize a molecule, when you take the infrared, you already have an idea of what you're looking for, and so the infrared basically confirms that, right? So these are all your different carbonyl stretches. All right, here's another common infrared stretch, the aromatic stretch. It's a weak stretch, shows up about 3,000 to 3,300 reciprocal centimeters. And then your nitrile stretch shows up somewhere between 2,000 and 2,300, and that's a very important stretch as well, right? All right, and then alkenes, that's kind of a weak stretch, medium stretch, 14 to 1,600. You can imagine that if you have an alkene present, it's very possible for that alkene stretch to overlap with the carbonyl stretch, because you're talking about a carbon-carbon pi bond, and so, or a carbon-oxygen pi bond, or a carbon-carbon pi bond. And so with that being said, a lot of times your alkenes, if they're in the presence of other functional groups, it's very difficult to tell those apart. If they overlap. Now, if they're not overlapping, you can look at the intensity and tell them apart. All right, ethers have a really strong stretch between 1,000 and 1,200, and that's your CO single bond stretch that shows up there. All right, so here's again, if you want to take a screenshot of the charts or write the values down, you can. But infrared is a very important tool in the analytical toolbox of an organic chemist, because again, it tells you what functional groups are present. And here's the rest of that list with alcohols, amines, nitriles, so on and so forth. And feel free to pause the video if you want to write down some of these values.